Looking around at the edge of a black hole, you will see 99 versions of yourself, and it's not magic. It's the photon sphere, the most amazing place in the known universe. Today, let's talk about a fascinating topic. What would happen if I threw you into a black hole? This is not science fiction. It's based on real physics. Before I throw you in, let's talk first. This black hole, which Einstein called a beast, what the hell is that? When a very dense star reaches the end of its life, it will collapse into a void. There's no surface to step on. There is no physical object to touch. It will eventually become something called a singularity. It's a mysterious point in space and time. It's said to have infinite density. Even its gravitational force becomes infinite. Einstein's general theory of relativity, it really flips our perception. Gravity, it's not really a force acting on objects. To put it bluntly, it's the mass of an object bending space-time. This theory perfectly explains why the Earth revolves around the sun. And here's what's interesting. Why are black holes so black that even light can't escape? Look at that. When you stare at this black hole, there's actually no physical entity in space. The black surface, the singularity hidden inside, it's incredibly dense, twisting space-time into a deep vertical well. So, don't even try to escape, not even light. Why? Because of such a strong gravitational force, escaping from its grasp, you have to run faster than light. Everyone knows this is impossible. Einstein worked this out. He didn't believe it himself. How could nature possibly allow it? Such outrageous things exist. In 1939, he also wrote specifically, the paper says, it's impossible for a collapse into a singularity to occur. It doesn't happen in the universe. The funny thing is, that same year, Oppenheimer and physicist Hartland Snyder published a paper, predicted stars could collapse into a black hole due to its own gravitational force. And here's the thing, anything can become a black hole. Yeah, I'm serious, even you can. German physicist Karl Schwarzschild, he was the first to solve Einstein's field equations. It's a very elegant solution. Basically, it doesn't matter if you are a star, planet, or even a person. Just take the mass m, compress it to the corresponding Schwarzschild radius, and there you go. A black hole is born. For example, if you cram all the mass of the sun into a radius 3 kilometers in a sphere, it turns black. The Earth has to be compressed into a 9mm radius sphere. It's about the size of a glass marble. As for humans, you'd have to be crushed much smaller than a proton. But if you could shrink that small, you could really become a black hole. I think it's time to send you into a black hole. But which black hole should we choose? Pick a small one, okay? That seems a little boring. Something exciting. Let's see how these big ones are doing. Their event horizons are larger than our entire solar system. That's the mass of billions of suns. But that's an exaggeration. Or find one closer to home, like Sagittarius A star at the center of the Milky Way, a supermassive black hole. It has been photographed by humans, one of only 2 black holes. We fly there in a spaceship, 1 trillion meters away from it. Then I send you toward the black hole. As you are in free fall, I'll be watching from the spaceship. But here's the thing. According to general relativity, space-time warps dramatically near the black hole. So, the time we experience will be completely different. To help you keep track of time, I'll give you a special watch. It shows the time you experience and the time I observe on the spacecraft. Let's check the watch first, and then you can continue your journey to the black hole. After you leave, you'll see a massive black hole in the distance, devouring matter like crazy. The friction makes it super hot. In reality, this accretion disk is actually bright blue, or even white, but for clarity, can you see it clearly? We've made it orange on purpose. You glance at your watch for the first time. It's only been 30 minutes. You have flown toward it. About 0.1% of the distance to the event horizon is completed. So far, my ship clock is only 11 seconds faster than yours. And now we're getting closer. Space-time warps around black holes start creating all kinds of magical effects. Even light from the sides and behind the black hole will bend around and reach your eyes. Take another look at the time. Now you've been gone for 2 hours. You've progressed 1.4% of the way. My clock is already 44 seconds faster than yours. But the black hole's shadow, the dark region in the middle, expands much faster than we expected. Due to gravitational lensing, light that should have passed by is all bent and reaches your retina. After some time, you finally glance at your watch again. For you, only 12 hours have passed. But on my side, the spaceship's monitoring screen shows a picture of you floating toward the black hole. For 15.5 hours, we are very close to our goal. But then things get really weird. Before you reach the event horizon, you will encounter a place that is both strange and magical. If you could pause in this magical place, let time stand still, then look around, your jaw would drop. You have reached the photon sphere. This could be in our universe, the most incredible place. This is a particular region around a black hole. The gravitational forces here are perfectly balanced. So light can actually orbit a black hole in circles. Whether it's light emitted by matter or reflected light, photons will stay in their orbit obediently. If a beam of light moves tangentially, it can orbit the black hole. But if the orbit is slightly off, photons will either fall into the black hole or fly off into space. In this extremely exceptional situation, if you stop at the photon sphere and look around, you will see a mirror image of yourself. With your eyes looking away, you will see the backs of countless versions of your own head. Looking into the distance, this is not some high-tech trick. You really see another version of yourself. Standing next to you, this is the magical effect of space-time warping. As you move forward, the event horizon is getting closer and closer. Now you've passed through the photon sphere. The black hole looks bigger than expected. It takes up almost your entire field of vision. It feels like you are about to be swallowed by the darkness, because the surrounding light is distorted. Not only can you see the scene in normal space, even the shadows on the back and sides of the black hole. You can see everything. It's been 13 hours since you left. In 24 minutes, you're going to cross the event horizon. But for me on the spaceship, I have been watching your journey for almost 20 hours. 18 minutes later, I check again. I've been watching you for almost 40 hours now. It's only been 18 minutes for you. For me, it was 18 hours. It's finally time. In 6 minutes, you are about to cross the event horizon. You close your eyes, take a deep breath, look down at the watch, but find it seems to be broken. The dial displays, "I've been watching you fall for centuries." In fact, the watch isn't broken. The laws of physics hold true. I did spend decades watching you approach the event horizon little by little. Then your whole body starts to glow red. I had to use an infrared telescope to see you. Even if I could live forever, I'll never see you actually cross the event horizon. At the moment you cross, the last 6 minutes of your journey seem like forever to me on the spaceship. This sounds like science fiction, right? But that's what Einstein's equations predict. Now you have crossed the event horizon. And here's the interesting thing. It's hard for you to perceive accurately. When you cross that boundary, you can still see the universe. You can see distant stars. You can even see our spaceship floating in outer space. But all this light, including yourself, is doomed to fall toward the singularity. You have nowhere to escape. At the singularity of infinite density, the laws of physics break down. Time will also stop. To escape the gravitational pull of the singularity, you would have to move faster than the speed of light. But that's simply impossible. Many people think at this moment, you would see the entire universe's future history fast-forwarded before your eyes. That's not true. Due to gravitational effects, as you approach the singularity, the outer universe will be compressed into a thin halo. Finally, when you get close enough to the singularity, your feet are stretched ahead of your body by gravitational forces. Your body is torn apart like noodles. This is known as spaghettification. At this moment, you and the black hole become one, forever part of the universe together.